we are going to do some enthalpy calculations. We have an equation here, a reaction. It's already balanced and ready to go. We know that there is energy stored in each of these compounds. That energy is used to create those compounds. That's why this energy is called the heat of formation. You will be given the how much heat is stored in each compound in a chart, or you can look it up in the back of your textbook. In this case, you're given that information. So you'll notice that for NH3, it has a negative number. That means that it is exothermic. In order to form that molecule, the NO2 has a positive number, therefore it's endothermic in order to form that compound. So, but this information is given to you. All right, so in order for us to calculate the total amount of heat either gained or lost in this reaction, the enthalpy of the reaction, we're going to use this formula. So it looks kind of weird, but let's walk through it. So we have the delta H, which is the change in heat of the reaction. And so in order to calculate this, we need to know the sum. This is the Greek letter sigma, and it means sum. So the sum of the heats of formation of the products. So we take, here are our products, so we're going to find the sum of all of this heat that's stored here minus the sum of the heats of formation of the reactant. So we're going to take the sum of all of this heat energy, add it all up, find the sum, and subtract it from the product. Now the little n here stands for moles, so we have to take into account how many moles of each compound we have, because this information is given to us in kilojoules per mole. So up here we have 4 moles, so we'll just have to multiply by 4. Okay, so once we break it down, it's really not too difficult. So first of all, we're going to find the sum of heats of formation of our products. So here are our products. So I have 4 moles of NO2. So I'm going to put 4 here. And NO2 is right here. The heat of formation for the NO2 is 34 kilojoules per mole. So I'm going to multiply by 34. Now I'm doing the sum, so I need to add. And I've got another product here, 6 moles of water. So I've got 6, and my moles of water is negative 286. So this, when I add these together, these will be the sum of my heats of formation of the products. Then I'm going to subtract all of this, and I need to find the sum of my heats of formation of my reactant. So I come over here, I have NH3, I've got 4 moles of it. The heat of formation of my NH3 is negative 46. I'm going to add that to 7 moles of oxygen. When you look on this chart, there's no oxygen. And why is that? Oxygen in its elemental state, any compound in its elemental state, when it's just that element, is going to be 0. So I have 7 moles, but its heat of formation is 0. Multiply that by 0. All right? And then literally I just punch that into my calculator. So I'm going to break this up. So I'm going to say 4 times 34 plus 6 times negative 286. And for my products, I get negative 1580. And I'm going to subtract from that the sum of my reactants. So clear that. I've got 4 times a negative 46. Well, let me try that. 4 negative 46 plus 0, because 7 times 0 is 0. So I'm subtracting, but I ended up with a negative 84. Excuse me, negative 184. So negative 1580 minus a negative 184. and I get negative 1396. And that number is my my enthalpy, my change in heat for this reaction. Now, it's a negative number, so what does that tell you? Was heat gained in this reaction, or was heat lost in the reaction? If it's a negative number, heat was lost. If heat's lost, it is exothermic. And that is how you work every single one of these problems. If your answer is positive, if you end up with a positive number, you're going to have a, it's going to be endothermic. Now, if we were just to sketch this graph, and we know that it is, we know our final heat here. This is what our products, we ended at negative 1580. We could just kind of sketch that down here, negative 1580. Our reactants went in at negative 184. This is definitely not to scale. All right, so we went in with this amount of energy. We'll just put a little bump for our activation energy. And we ended up somewhere down here. Okay, so we can see that it is an exothermic reaction. If we wanted to label our delta H, it would be from, here are your reactants. I'll put an R there. This would be your products. Oops. Your products here. And so your delta H would be the difference between these. So the delta H would be negative 1396 kilojoules per